in St. Petersburg, whatever, right? It could be anywhere. So if you make that table, you're going to have time and then your position, right? So at time equals 0, what is it saying for part E? Where are you? For part E, where are you at time equals 0? At home. So what's your position? 0. Okay. So at time equals 5, how far have you traveled? Nope. This is velocity, everybody. No. 10. Let's go with answer number 3. Okay, 10, right? And then at the numbers are filled in there. Can you see them? I'm trying to make it big enough that I can write too. So at 10, how far have you gone at 10? 30, right? And then at 15, how far have you gone? 55. So can you fill in the rest of these like this? So what you do is you graph those points. So you see all those points right there? So what do you see there? 10, 30, 55, right? And you graph them. But what's it also asking you to do? Draw the distance for the first 35 seconds. Be sure to indicate concavity. Concavity is related to which derivative? The second derivative. Okay, so you have position. Velocity is the first derivative of position. Second derivative would be the derivative of this, the acceleration, right? And remember, so if a of t is positive, then what? It is concave up. And if a of t is negative, and then it's what? Concave down, right? So for each of these segments, what can you figure out? Concavity. So what's going on here, here, at those two yellow places? What's going on there? A of t is what? A of t is greater than 0 because the derivative is positive, right? Let's do the other ones now. Let's do the negative ones here. So are there ones that are where it's going negative? Sure. There's here and here, right? So what's going on there? A of t is less than 0, so it's concave down. And then what's going on what's going on here, though? What's interesting? So what's going on? Sorry, that is not what I wanted to do. Excuse me. What's going on right here and here? A of t is what? Maintain the same speed. So here and here, A of t is equal to 0, right? So you go down here and what do you see? What do you see here? You see, I think you have concave up, right? Sorry, trying to get the highlighter here. You get concave up right there. And where else do you see concave up? Right there, correct? And then you also see, and then there's concave down where? At the end, right? At the end. So the concave down is right here. And then what's going to happen on those other segments? What are you going to see? Straight lines. What color did I use? Blue? I think so. Straight lines, right? Does that kind of make sense? That's what it's saying. So it correlates as such. So you have A of t is positive here. You have A of t is negative right there. And then you have on those two segments, A of t is 0. So that's concave up, and this is concave down, and then this is linear. Does that make sense? Is that cool? Any others? So when you do an integral, what was the first way we learned how to do an integral? So if I gave you originally, let's say I gave you, where's cosine start? It starts up at 1, right? So let's say that was the first part of cosine, 0, whatever. Let's say that's the first part of cosine, right? Cosine x, nice. And what's it here? That's x equals what? Pi over 2, right? Correct? Is that right? Okay, so if I had asked you right when we first started looking at integrals, if I asked you, please find me the area under the curve, so find me this integral, 0 to pi over 2 of cosine x dx, you only had a way of estimating that, right? How did you estimate it?
Like the left hand, the Riemann sum.
Riemann sums, so rectangles, right? And could we get pretty accurate? How did we get more and more accurate? More rectangles. Calculators are really good at doing basic operations. What's a basic operation? Multiplying, dividing, subtracting, right? Riemann sums are effectively what? Multiplying and adding things together, right? How fast can calculators do operations? Pretty fast, right? So they can make some rectangles and come up with an estimate, right? And then to make a better estimate, what can they do? Make more rectangles, 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 right? And they can get to a point, where it's good enough for us, right? It's good enough for us. The key realization here is this. Calculators are doing this. Your calculator is doing that type. When you ask it to do this integral, you like to think of it as giving you like that Riemann sum program, right? It gives you an estimate, right? But can you do, there's this fn int. Do you remember you learned how to do that with Mrs. McCullough, right? You did put in the 4 things and then you get the exact answer. Is the calculator actually giving you the exact answer? It's not actually doing that because look, you get answers something like this, like 15.667, When the calculator gives you that, generally what is it actually saying the answer is? 15 and 2/3, right? The calculator is just estimating to a really, really high degree of accuracy. And when I say high degree, it's all relative, right? So accurate enough for all of us, right? Does the calculator actually do calculus? Does it compute the integral of cosine and say it's sine? No, it doesn't. It doesn't actually do algebraic manipulation. It doesn't do algebraic manipulation. It's just doing really, 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 really good estimates that are really good for us, to use the Zoolander intonation. That kind of makes sense? So when your calculator spits out something like this, most of the time what you want to translate that to is 0. Sometimes it's not. Be careful. Sometimes it's not, and those are some nasty questions I can ask you, right? You know, like some functions get really close to 0 but never get to 0. Like you could have a horizontal asymptote at y equals like 1/1,000,000th, right? And that would be like, dang it, that's kind of annoying, right? But the point is, in general, when you ask your calculator to do an operation and it comes out to something like that, -3.0 times 10 to the -13th, it's 0. Does that make sense? You still have s of 0, right? Plus what? Integral from 0 to 8 of v of t dt, right? And then what about 12? S of 0 plus what? 0 to 12. Yep. So what's the only thing that changes? Oh, just the time index, right? You need that initial position, though. It says, write an integral expression that represents the total distance the person traveled in the 12 seconds and then evaluate this. So I want you to see if you can figure this one out. Take a look at what we've done and then see if you can figure out what the integral Why not?
Because that's negative and positive, right?
So what is that represents what? Kind of displacement with the initial position, with the 5 in there. So just this would be displacement, right? So what do you have to change to get the total distance traveled? What? Of what? So what's the integral? It's going to be the integral from
0 to 12.
Of what?
Absolute value of v of t.
Exactly, absolute value of v of t dt. Now, do I put the s of 0 in front? Do I put that in front? If I just want the total distance traveled, does it have anything to do with where I start or where I end? No, the 5 isn't in there. So if you want the total distance traveled, you just do the absolute value and you integrate that from 0 to 12. Do that on your calculator and see if you can figure out where it is. What the displacement, sorry, what the total distance. Are you plugging in y1 as this? Yeah, you can do y1 abs and then v of t, like that, whatever, however you want to type it in. ABS works. You know, the bars will also show up. It depends on which version you have running. So it'll either show up as ABS or literally just that. That's fine too. Either one is good. It just depends on which version of the operating system is installed. Okay. Exactly. So you need to actually find, you have to do the f of, so it's going to be f of 4, right? Minus f of -2. So what do you have to find in order to do this one? So this is, if that's s of t, what do you have to find?
S of 4 and s of negative.
Yeah, in order to find s of 4 and s of 2, what do you have to find first? Oh, look, it actually gives you s, right? Does it actually give you s?
Where's S?
Literally written right above where I wrote the blue marker.
No, I mean like in the equation.
Right here.
Oh, okay.
It's literally right there. So they actually give you the integral right there. They tell you the antiderivative. They tell you it right there. They tell you it.
Oh, okay.
They tell you the position function. Is this the same as this? Uh-huh. So are they actually telling you the integral? Are they telling you the antiderivative? So in order to do this, you need to do s of 4. So it's going to be 4 times 4 cubed minus 2 times 4 squared plus 3 times 4 minus 1. And then what do you subtract from that? Help me out here. Then what do you subtract from it? 4 times -2 cubed minus squared?
Yeah.
It's cubed. No. Times -2 squared plus 3 times what? -2 minus 1, right? Is that something you theoretically could do by hand right there? What's the really nice thing they told you right here? What's the really nice? They told you the antiderivative. Now, is that something you're always going to get? No, not at all, especially with polynomials. We went through, I gave you a little preview of what's to come. Did we actually do the antiderivatives of things just like this? Yeah, absolutely. Absolutely. So let's say I gave you, let's say I just gave you this. Let's say I said, okay, what about, hold on, let me do this. What do you need to find first? What do you need to find first? The what? The antiderivative. Can someone tell me what the antiderivative of 9x squared is? What's the antiderivative of 9x squared? It's going to be x to the what power? 3, right? But what has to go out front in order to turn it into a 9? A 3, right. No, a 3, because you want to turn it into a 9, right? You drop the 3 to the front. What's 3 times 3? 9. We're not trying to get rid of the 3 this time. We're trying to turn it into a 9. Can you tell me, and it's 12x, sorry. 12x right there. Can someone tell me what the antiderivative of 12x is? Well, it's going to be x to the what power?
6x squared.
Oh, 6x squared. And what about minus 4? What's that going to be? What's the antiderivative of that going to be? Minus 4x, exactly. And I'm going to give you some notation, everybody. This bar from 0 to 2, what do you think that means? That means you evaluate it from 0 to 2 and subtract. That's the short way of notarizing it. So what do you plug in first? You plug in 2. 3 times 2 cubed plus 6 times minus 4 times 2, right? And then what do you subtract?
0.
Yeah, 3 times 0 plus 6 times 0. Just because you're plugging in 0 doesn't necessarily mean you're going to get 0, but sometimes you will. So could you finish that right there? Do you understand the pieces?
Yeah.
You're going to do this a lot. This notation right here, you see this bar right here? That is super, super, super common. We're going to use that a ton, almost as much as we use this. Almost as much, yes.
What does that mean exactly?
It means evaluate from 0 to 2. This right here is the same, it means do this.
Alright.
It's the shorthand way of saying what we started up here. Let's get back here. This right here. See this? Right? Just the beginning part right here. It means do that. It means evaluate, plug in B, and then subtract what you get when you plug in A. That's all it means. Mathematicians love this right here is just evaluating the function, right? So given f below. So keep in mind, this is the function of f, right? Lowercase f. So f of 2.5, where is that? Well, looks like that's right about, I don't know, like, it's like, oh, sorry, that would help, yes. So where's f of 2.5? You go to 2.5, it's like right about, I don't know, here, right? There's f of 2.5, right? Do you agree?
Yeah.
Where's f of 5? What does it look like f of 5 is?
0.
Yeah, it looks like f of 5 is 0. It looks like this is 0, and this is about 1, 2, 3. This one looks like it's about 5, right? So which one's bigger? F of 2.5 seems to be greater than f of 5. Now, is B asking for the same thing?
No.
No, what is B asking for? It's capital F? Capital F. Be really careful. Is that derivative? Is that derivative? Is that derivative? No, it is antiderivative. It's the other way. So take a look at that and see if you can come up with which one of these is greater. Because when you, sorry, thank you. When you take the integral, you don't know how high up you're going to be. You don't know how high up you're going to be. You do know, you could think about it in a way that like, so for example, all you know is that f prime of 2.5, f prime of 2.5 has to be about 5. That's all you really know. But you don't really know what f is, where you started. So let's do it this way instead. I'll ask you this question. The integral from 0 to 2.5 of lowercase f of t dt compared to the integral from 0 to 5 of lowercase f of t dt. Let's say I changed it to that. Let's say I changed it to that right there. What do we know? We know this, for example. That. So we get 0 to 2.5 of f of t dt equals f of what? 2.5 minus what? F of 0. You with me so far? Okay, so if I wanted f of 2.5, let's say I wanted that, can I isolate f of 2.5?
Yeah.
Can I isolate it? Sure. What is f of 2.5 going to be equal to, Natalie? F of 0 plus what? Integral from 0 to 2.5 of dt. So similarly, what's f of 5 going to be equal to? F of 0 plus what? 0 to 5 of f of t dt. Okay, so we don't know what they actually are, but we can compare them because if we want to compare f of 2.5 and f of 5, first of all, raise your hand. Are you okay with these two statements right here? Are we okay with them? We good? So if we're comparing two things and they have the same thing in there, for comparative purposes, can we just ignore these two? Like if we're balancing a scale, right? We want to compare the size of two things. We're going to have 10 pounds and 10 pounds. Can I just eliminate those 10 pounds for comparison?
Sure.
So it's entirely going to come out to be this right here. F of 2.5, f of 5 comes down to these two things, comparing them, right? So this is the area under the curve from 0 to 5, and this is the area under the curve from 0 to what? Oh, so we don't know what the actual number is, but we can compare them because let's go back here. What's bigger, the area from here to here or all the way to 5? What's bigger? All the way to 5 is bigger. All the way to 5 is bigger. Looks like roughly twice as big, right? So we don't know what the actual number is, but can we compare these things? Like, do we have any idea what f of 0 is? No, we don't. We don't. We can compare them. What about 5 or 10? It's the same idea here. Be really careful. Everybody, take a look at this. This is really, really important here. F of 5 or f of 10?
They're equal.
Are they equal? Are you sure?
No, do 5 because.
Why is 5 bigger?
Because to 10 has the negative space.
Exactly. It's going to take it away, right? When you run the
that's
integral,
capital F again.
exactly, when you run the integral of this, right, lowercase t like this, part of that is going to be negative and part of it's positive, right?
Yeah.
The f of 5 is the positive part. So which one's bigger? Capital F of 5. Does that make sense, everybody? What about this one? 10 or 15? Which one's bigger? Which one's bigger? 15, because 15 is the same as 10 adding some positive in. They're equal up until this point. F of 10 stops and f of 15 keeps going. Does that make sense?